kind of jump in. I will post the chapter 5 homework. I will make that available later today. It's not up just yet, so after we, lecture on some of this, I'll get that up on Mastering Chemistry. And then remember, if you've not yet completed your chapter 4 homework, when is that due? Yes, tomorrow at the end of the day. Okay, so go ahead and get it done so that it's not hanging around on your to-do list on a Friday. Any questions from anybody before we get into this? No? Okay, are y'all awake? No? I had a small cup of coffee. That's all I had time for this morning. So we'll see if I'm awake too. I hope I am. All right. My 8-month-old is in the habit of waking up at 5:30. It's like clockwork every morning, and he's hungry. So that's when I get up these days. Let me share my screen. Okay, new hike. We're still in Tennessee. I think if you remember from chapter 4, if you watched that lecture video, I talked about Cummins Falls, and that was a really cool hike around the Nashville area. This one's another one around the Nashville area. I have one or two. This might be the last one. I can't remember. From our Nashville trip, and it was awesome. So if you have not visited Nashville, if you're like, where should I go on spring break and I need a cool place to go, Nashville, Tennessee, if you've not ever gone, is such a cool city. So many great places to eat. There's just great hiking around. There's such like an incredible shopping center in Franklin, Tennessee, which is really not far from Nashville. So many things. I cannot talk about Nashville enough. And they are home to, anybody ever had, it's called a cronut, a croissant donut. They call them 100-layer donuts. Anybody ever had one of those before? I need to pull the chat up. I will always find an excuse to talk about food, and especially in the mornings. Breakfast is my favorite. If you skip breakfast, you're doing it all wrong, okay? Anyways, Nashville has a place called Five Daughters Bakery. You should seriously write that down and go as soon as you get the chance to. But anyways, this is a hike we did in Tennessee, not far from Nashville, about an hour-and-a-half drive. And it was called the Walls of Jericho. It's probably a good 9-mile hike. So this one was like an all-day thing. And it was down a lot of the way there and up a lot of the way back. So, but it was so much fun. And we hiked down here, and a lot of people get to this little spot and they're like, oh, cool, a little pond. And there's no it doesn't feel like a grand finale at all. But there is a little teeny waterfall you can see. So we ate lunch here. Well, my husband had done some research. Oh, Kylie says she's been there and it's yummy. Okay, I promise you, you will never want a regular donut again after you have a 100-layer donut. It'll ruin you. Anyways, my husband had done some research, and there was a hidden waterfall that you have to hike back to. So a lot of people get here and they don't see the cool stuff that you have to hike a little further to see. So we actually hiked. I don't know if you're going to be able to see this, back in here. Okay, back up behind this little river waterfall area. So there were some rocks kind of over here. You can see we crossed over there and hiked back up in here. And this is the view looking down on the picture you just saw. And we hiked a little further back, and there was a hidden waterfall that you don't see unless you hike to it. Why is no one's jaws dropping? Okay, this was so cool. Anyways, it was actually bigger than it looks, and it runs through all of this rock right here. This water does, and that's what you see coming out, right in here. So it was really, really cool hike. We had a lot of fun with it. But enough about hiking and food. How about we just talk about that all day today? Our favorite restaurants, favorite things to do outside of school. I would love to. But we're going to talk about chemical reactions, chapter 5. So cover the first half of this today. Here's the goals for today. We're going to learn how to write chemical reactions. We're going to learn how to balance them. And then we're also going to start recognizing different types. And here's why this is important. Right here, this is going to help us predict products of a chemical reaction. Okay, so if I give you two reactants and I say write the products, if you get number 3 well, if you understand it well, then you'll be able to do that just fine. Okay, there's 5 preliminary type of reactions we're going to look at today, and then next week, I guess we'll look at 3 more in-depth different classifications of chemical reactions. They're going to be a little bit more tough. So please, if you have questions after we go over these 5 classifications today, let me know, because Tuesday we're really going to get in depth with 3 more. I think they're some of the most difficult stuff we cover when it comes to chemical reactions. So, all right, if we're going to talk about chemical reactions, let me continue talking about food for a second. It's kind of like a good recipe. Anybody, like, you love to cook? Anybody, you like to stay at home? It's way cheaper, by the way. I know it takes more time to grocery shop and cook your own food. But you can do it if you have a good recipe, right? Some of you can get in there and you can just throw things together and it turns out somehow, right? But I'm usually pretty good if I have a good recipe. Okay. Thank you, Joanna Gaines, for sharing all your good recipes with us. But anyways, you need a good recipe. What does a good recipe include? Okay. I don't care. Think about your favorite recipe, cookies. I don't care. Breakfast. You need to know how much of each ingredient to use. You need to know what to do to the ingredients, what order to mix them in. And you need to know how much of the final product you're going to get. Okay. Especially if you're like cooking for people. I'm a huge fan of leftovers. Okay. So I always like double the recipe so that I get leftovers and I don't have to cook every single night. So these are the things we need to know. And this is the exact same type of thing a chemical reaction tells us. So for example, let's talk about the recipe for a s'more. Okay. RIP to winter and bonfires and s'mores until next winter. But what's the recipe for a s'more? What do you need for a s'more? Somebody tell me.
Graham crackers, chocolate, marshmallow.
Okay, so we need graham cracker. I'm going to abbreviate. Plus chocolate. Plus marshmallow. I'm going to abbreviate. All right. And if you really want to do it right, you'll put some mayonnaise on it. Okay, I promise. Trust me. I'm just kidding, guys. Do not put mayonnaise on your s'more. I didn't even do that when I was pregnant. Okay, that's disgusting. All right, and this will give you 1 s'more. So this is not as specific as we can get though, right? How many graham crackers, how much chocolate, and how many marshmallows? I'm sure this is where the recipe would vary, but a detailed recipe would tell us, okay, 2 graham crackers, 1 small bar of chocolate or whatever. You might write half a bar of chocolate. I don't know how much you put. And then 1 marshmallow, right? I'm definitely a 2 marshmallow kind of person, but everybody probably, you can be specific is all I'm trying to say. And then I don't know about you, but I add some heat, tell you what to do to the ingredients, and that's going to give me 1 final s'more, right? So you see how specific you can get. This is exactly the way a chemical reaction is. It tells us how much of each ingredient, it tells us what to do to it, and it tells us how much of the final product we're going to get, okay? So let's look at a real example of a chemical reaction, one that applies to you and me every single day, especially in a health science sort of realm. I'm going to read this sentence right here. Carbonic acid in low pH environments breaks down into bicarbonate ion. You guys should recognize that bicarbonate ion is HCO3 minus and a hydrogen ion, okay? And this is the representation chemically of that word sentence, okay? This is the reaction representation of that. Carbonic acid right here in low pH environments breaks down into bicarb and H+, okay? Anybody know what this reaction is important for? Why is it important to us in a health science realm? This is responsible for maintaining the pH of your, anybody know? Yep, thank you, Bailey. Keeps our blood pH normal. Okay, anybody know what physiological blood pH is? What is the pH? It's actually a small range. There's a little bit of fluctuation, but it's not a big range. What is physiological pH? Come on, y'all need to know this. Thank you, Rachel. Yep, it's right around 7.45 to 7.35. Okay, so we know a pH of 7. If you've heard anything about pH, we're going to talk a whole lot about pH later. But pH of 7 is neutral. So you can see it's pretty neutral, slightly on the acidic, or sorry, slightly on the basic alkaline side. But your blood uses this reaction right here, carbonic acid and bicarb. And then there's a little bit more to it. We'll see later. But to keep your blood pH in the range that it's supposed to be. If your blood pH falls too acidic, you'll go into a coma. And so it's it's essential that your body is efficient. This is very important to you. All right, let's label the different parts that I have arrows pointing to. I bet you can already do that. The first blank is pointing to H2CO3. We call this a reactant. Put an abbreviation S. These are substances that undergo the chemical change. Okay, these are what are changing. And then the products. These are the substances formed in a chemical reaction. So you've probably heard of that, reactants and products. Nothing new there, but those are the basic parts. And I will tell you, the reactants are always on the left and the products are always on the right. So you always draw the arrow pointing from left to the right and you read it like a sentence. Okay, one thing I want to mention, we've talked about this before when we talked about Dalton's atomic theory. You guys remember Dalton's atomic theory? We said atoms are not created or destroyed. When we do a chemical reaction, they're just recycled. And that's what this is getting at here. Bonds, ionic or covalent, doesn't matter. You could have both or one or the other. They are rearranged in chemical reactions to make new compounds, but atoms are not created or destroyed. We just rearrange them into new things, okay? And so this is going to kind of set a principle that you always have to make sure. This is why we have to balance chemical reactions, and I'll hit more on that in just a second. But we don't destroy anything. We just rearrange stuff to get our products. Everything on the reactant side should be on the product side, maybe just rearranged. All right, another thing about chemical reactions before we actually get into some balancing is they often include the physical state.
Wait, like, can you go back up just right quick? I was on like the test one.
For sure. No problem.
Sorry about that.
No, good, you're good. Chemical reactions often include the physical state of reactants and products, okay? So you can see if you're looking at this reaction right down here, sodium bicarbonate plus heat makes all this different stuff. These little abbreviations that I'm underlining, S, S, L, G, you might have wondered, maybe you've seen something like that before, what it stands for. These are telling you if it's a solid, a liquid, a gas, so on and so forth, okay? So the four things you could see for solid, obviously, is the abbreviation of an S for a liquid. You'll see an L for a gas, if something is a gas, obviously a G. But there's one more I want. Anybody seen a fourth one before? There's one more that you'll see sometimes in a chemical reaction. Maybe some of you have seen it or know what I'm about to write. AQ, AQ. Okay, what does AQ stand for? Yeah, you will see this one. Aqueous, aqueous. People say it different ways. I say aqueous. Okay, but what does that mean? Why do we have aqueous, and how is that different from solid, liquid, or gas? Is this a forced state of matter? No, it's not a forced state of matter. What does aqueous mean? Obviously, it's different, so we have to denote it differently. Aqueous is something that is dissolved, okay? It is a solution. And it has the compound that is aqueous is dissolved in liquid. Okay, so here's a great example. If you have NaCl and it's a solid, we know salt, you can pour it into your hand, little salt crystals. The moment you put it in some warm water and stir it up, you are going to have, I'm actually going to move this over. You're going to have, you could write this, NaCl aqueous, okay? But what's actually happening is you're going to have, it's dissolving into its ions, Na plus and Cl minus. and those are distributed throughout the water in the solution, okay? So if you read something that's aqueous, know that it's actually dissolving, breaking down, if it can, into ions. We know ionic compounds break down into ions, okay? Covalent compounds, they don't break down into ions, but they can dissolve, okay? Like a molecule of sucrose, sugar. You could have a big hunk of millions and millions of molecules of sucrose put together, and then you put that in some warm water or some hot tea or some hot coffee. It's going to dissolve into small individual molecules of sucrose, and we would still call that aqueous. Okay, so it's just something that's dissolving in solution. All right, so I just wanted to point those out. And then what we said earlier about atoms not being created or destroyed, this is actually a law, the law of conservation of matter. Or it might be the law of conservation of mass. Sorry. Because the definition says mass is neither created or destroyed in chemical reactions. Okay. And atoms take up mass. So, all right. So what this law means, and the reason we have to pay attention to this is because we have to have the implication here, right here, is that we have to have the same number and kind of atoms on the product side as we do the reactant side. So this is where we're going to start learning about balancing. Because atoms are not created or destroyed, because the law of conservation of mass is a real thing for any chemical reaction, we have to balance them. So that means we have to have the same number of atom X on the reactant side as we do atom X on the product side. All right. And you apply that to every atom in your reaction. So we're going to look at a first example, and then we're going to do a lot of practice problems. We have sodium bicarbonate. And I want you to get comfortable with learning how to say things. And I just realized I did not go back and do an example of naming binary compounds. I'll try to save some time at the end of lecture day to review a little bit of that video, 10-minute video lecture on naming binary compounds that I posted, because I'd love for us to go over that together. So I want you to get comfortable saying the names of compounds. You had to write the names of them on exam 1. And I want you to get comfortable saying them. So if we're reading this reaction, I would say sodium bicarbonate breaks down into sodium carbonate. You could name that, plus water, plus carbon dioxide. Okay. Now, looking at this reaction, you ask yourself, do I have the same number of every kind of atom on my reactant side as I do the product side? So the first one we'll start with is just sodium right here. How many sodium atoms do I have on the reactant side right now? Looking at this formula, I just have 1, right? Now, looking at the product side, how many do we have on the product side? Yep, thank you, Kyla. We have 2 right there. And if I had it in another compound, I would have to add it up for that compound too, total across any compound that it appears in, but it only appears in sodium carbonate here. So this is an issue. I've got 1 sodium on the reactant side, 2 on the product side. What am I going to do? Well, this is where balancing comes into play. And the way you balance is with numbers out front, just like we did with the s'mores recipe. We put like a 1 graham cracker or 2 graham crackers and 1 chocolate. You put numbers out front to change the number of compounds or atoms on the side that you need more of. Okay, so we could put a 2 right here in front of sodium bicarbonate. Now what that 2 does, this 2 multiplies everything in this compound by 2. So now we have 2 sodium atoms. Now we have 2 hydrogens. Now we have 2 carbons. And now we have 2 times 3, because we got 3 oxygens in carbonate. Now we got 6 oxygen atoms, all on the reactant side. Okay, so it multiplies everything in the compound by 2. All right. So now, does everything add up? Well, we got 2 sodiums and 2 sodiums, so that's good. We got 2 hydrogens, and I see 2 hydrogens over here on my product side as well, and that's the only place hydrogen appears. Okay, what about carbon? I got 2 carbons on my reactant side. There's 1 carbon, and there's another carbon on the product side, so that makes 2, so we're good. And oxygens, I got 6 on the reactant side. Does everybody understand how I added up 6 or multiplied to get 6?
Can you do it again?
The reason I'm saying we have 6 oxygens is because this 3 right here tells me I've got 3 oxygens in sodium bicarbonate. And because I have a 2 out front, I did 2 times 3 means I've got 6 oxygens. Does that make sense, Glenn?
Yeah,
I know
but
this
like, what
looks
about for like the first
confusing,
one?
but the first one, 2 sodiums.
Yeah.
Well, I've got 1 sodium in my compound right here.
Okay.
I don't have any subscripts that tell me I have more than 1. So when I put a 2 out front, that just means now I multiply that by 2. So if I had 1 originally, times 2 gives me 2 sodiums. And you do
Yeah.
that for every atom. I went through and did it for hydrogen, carbon, and oxygen. All right. So if I've got 6 oxygens on the reactant side, do I have 6 over here? Well, I've got to look at all my compounds. Here's what I noticed. Look at this. It's crazy. I got oxygen in every single compound. Okay, so I've got 3 oxygens here, and I've got 1 more right here, and I've got 2 more right here. So what is 3 plus 1 plus 2 gives me 6 oxygens. So everything is balanced. Okay, so if you've got an atom that appears in multiple compounds, you have to add it up across all the compounds. All right, and if I had coefficients over here, that would make it even crazier. I don't need 1 in this case, but if you did, you've got to multiply and add everything. All right, and we're doing this number, this little 2 that I put right here in front of sodium bicarbonate, we call this, anybody know what we call that? Numbers that we place out front. Yes, thank you, Pernille. We call it a coefficient. Okay, so coefficients are numbers placed in front of a formula, okay? In front of a formula to balance the equation and to make sure you have the same number and kind of every type of atom on the reactant and product side. So that is how you balance. You can never, ever, ever, let me erase for a second. For example, if I needed, knowing now that what we just did, we recognize we needed to make 2 sodiums on the reactant side, okay? Because this first reaction up here was not balanced. I can never go in and just put a 2 right here as a subscript and balance it that way. You cannot balance with subscripts, okay? Because that messes with your formula and that gives you an incorrect formula for your compound, okay? The formulas are set. You write correct formulas. You balance with coefficients, all right? You can never balance with subscripts. All right, okay. Then the final balanced equation, okay? You might hear me say balanced reaction, balanced equation, same thing. Means that you end up with the same number of each type of atom in both the reactants and the products, all right? So now that we've looked at how to balance, we're gonna do some practice problems. Questions so far? If you do have questions and you're not sure what to ask, then hopefully these next several slides will help you work those out. Okay, so like I said, I want you to get comfortable with saying compounds and reading reactions in your head. So how would you say the following reaction? Like, what does it mean? What's actually physically happening? So I want you to read this. I want you to say the names of the compounds. So I'll do this one with you. Potassium sulfate. That's how we would read that compound, K2SO4, potassium sulfate, plus, what's this one? Anybody can say it for us? You might need a periodic table with you. Why wouldn't we put di in front? Bailey has an excellent question. Why did I not say potassium or dipotassium sulfate? Because this is not a covalently bonded compound. This is an ionic compound. How did I know it was an ionic compound? Anybody? That's going to change how you name it if it's covalent or ionic. Sulfate, yes, sulfate's in it. But remember, ionic compounds are made of a metal and a non-metal. Ionic is a metal plus a non-metal. Covalent is 2 non-metals, usually, okay? So that is how I chose to name it as an ionic compound. So that's why I did not say dipotassium sulfate. It's just potassium sulfate. And I don't have to include Roman numerals or anything because remember this potassium is a cation that's a main group cation. So do not forget rules for how to name things. It's all going to play a part into chapter 5 when we write out chemical reactions and balance them. All right, I'm going to make this smaller so I have room to write my reaction and balance, like what I want it to do. So potassium sulfate, how would we name this second one? This is also an ionic compound. Ba is a cation from, I believe, main group 2.
Barium chloride.
Yes, chloride. Remember, IDE at the end is how you name anions. Barium chloride. So potassium sulfate and barium chloride make potassium chloride and barium sulfate. So things just switched around. So that's how you would say it. Now the question is it balanced? Y'all look at this really closely. Is it balanced? Do we have the same number and kind of atoms on both sides? No, 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 no. Okay, so what do we need to do? Let's just start with the very first atom. I see that I have 2 potassiums here. Bailey said add a coefficient of 2 to potassium chloride. So we're going to put a coefficient of 2. We have 2 potassiums right here. We need to have 2 over here. I only have 1. So I'm going to put a coefficient of 2. And that's going to give me 2 potassiums on both sides now. Okay, do I need to do anything else or is it fully balanced now? Same number of sulfate, polyatomic ions, same number of bariums. It looks like we're good. Okay. And if you ever want to double check yourself, you can write out all the elements you have down here, K, Cl. If you have a polyatomic on both sides, you can write it as a unit. So SO4 and Ba. And you say, okay, on my reactant side, I have 2. Product side, I also have 2. Chlorine, on the reactant side, I have 2. Product side, I now have 2. Sulfate, 1 and 1. Barium, I've got 1 on the reactant side, 1. That's how I like to do it. And that's how I just double check myself, okay? Questions on what we just did? So that was a very simple one. We just had to add 1 coefficient. I promise you it will get more difficult than that.
Wait, like, so how did you get the 2 on like the other side of the equation? Again?
How did I put a 2 right here? How did I know to do that?
Yeah.
I just started with my very first atom that I see on the reactant side. And I said, how many potassium ions do I have? And this 2 right here told me that I have 2 of those. Okay, so I've got 2 on the reactant side, which means I have to have 2 on the product side. So the only way I can make that happen is by putting a coefficient of 2 in front, because remember, we cannot put subscripts down here. We cannot balance with subscripts. KCl is the correct formula. We have to keep it KCl. So I had to just put a coefficient of 2 in front, and now I have 2 on both sides. Does that make sense, Glenn? Okay, I hope it makes sense. Let me know if it doesn't.
Yeah.
Okay, we're gonna look at some more examples. So if you're still like, that's what I expect you to be kind of unsure. This is new for a lot of people. All right, so here's the rules for balancing chemical reactions. There's 3 or 4. And again, you don't have to always abide by these if you kind of have seen this before and know what you're doing and want to just go for it. But if this is brand new to you, use these rules, these numbered rules as a guideline to balance chemical reactions until you get comfortable with it. Rule number 1, the first thing you have to always do is write the unbalanced equation. So if I give you a sentence, we're going to read this one right here in just a second and write it out. You have to first write correct formulas. That is the first thing I want you to focus on. If your formulas are not correct, then you're not gonna be able to balance it. Okay. So the first thing you have to do when writing out a chemical reaction is write correct formulas. And you know how to write ionic formulas for ionic compounds. And you know how to write formulas for covalent compounds. That's what we've done in chapters 3 and 4. Okay, so if you are unsure and need to go back and review, how do I write a correct formula for an ionic compound or covalent? Please go back and review that or reach out to me or brush up on that, because if not, your balanced chemical reactions are going to be very, very difficult to do. And then one thing that's very important when you're writing correct formulas is you have to remember why, which elements are diatomics. Okay. So remember there was a slide in our chapter 4. I'm going to scroll up to the diatomic slide. This is where we talked about diatomics. It was the video lecture that I posted the week of snow. So right here. Okay, this is where we had a whole slide on what atoms are diatomics. And this figure from your textbook tells you there's 7 elements that are diatomics. You have to write these as you see them on the slide. So if I'm writing hydrogen in a chemical reaction and hydrogen is by itself, I'm just writing elemental hydrogen, I have to write H2 and not H. Okay, I have to write H2, and same goes for all these others that you see. Nitrogen, oxygen, and the halogens, all right? So that's why that's important. Okay, so let's write this one. Hydrogen sulfate, I want you to write this out. Hydrogen sulfate, that's a compound. It's an ionic compound. Reacts with sodium hydroxide. There's another ionic compound. And then you're gonna draw your arrow. So these are your reactants. I'm gonna put an R above them for reactants. To make sodium sulfate, that's a product, and water is a product. Hydrogen sulfate and sodium hydroxide, and then draw your arrow, make sodium sulfate plus water. Okay, if you do not know what to write right now and you're very confused, then that's a key sign. You probably need to go back to chapter 3 and review the rules for writing formulas for ionic compounds. So hydrogen sulfate. Sulfate is SO4. This is a polyatomic. And remember, I asked you to memorize 11 polyatomics. So SO4, we know it has a -2 charge, right? Hydrogen is the cation here. Hydrogen is main group 1. So it has 1 valence. When it gives that away, it forms a cation with a +1 charge. So if I'm going to write a balanced compound, remember it has to be charge neutral overall, I've got to have 2 of these and 1 of these. So when I put those, you can do the switch trick. Remember, when I put those together in a compound, it'll be H2SO4. That's hydrogen sulfate. All right, reacts with sodium hydroxide. Sodium is Na. It's got a +1 charge. Hydroxide is a polyatomic as well. It's got a -1 charge up here. So I just need 1 of each. So NaOH. All right, so these are my 2 reactants. They react to make sodium sulfate. Okay, sodium is Na+, sulfate SO4 -2. So again, you do the switch trick. I'm going to need Na2, 2 of those, SO4. That is sodium sulfate. I'm going to make it a little smaller and leave room for plus water, H2O. All right, so there is my chemical reaction. So again, if you didn't write the formulas correct, you have no hopes of balancing it correctly. All right, now we need to go about balancing it. So anybody have any suggestions what we need to do? Remember, if you have a polyatomic that is present on both sides, you just treat it as a unit. So what that means, I've got sulfate is a polyatomic on the reactant and the product side. So don't break up the sulfur and the oxygen and try to balance those separately. Just balance it. How many sulfates do I have on my reactant side? How many sulfates do I need on my product side? Okay. Any suggestions on what we can do first to balance this? You need 2 sodiums on the reactant side. Yep, Rachel says start with sodium. So you guys noticed I have 2 sodiums on the product side. So that means I need 2 on the reactant side. And the only way I can make that happen is by putting a coefficient of 2 out in front. Okay, then what?
2 by the water.
2 by water. Okay. Zoe, why 2 by water?
I don't know. I think it needs it.
I think you're right, but here's why. Zoe noticed we have 2 hydrogens here and this coefficient of 2 multiplied hydrogen. So we've got 2 more hydrogens here. So 2 hydrogens here plus 2 hydrogen there is a total of 4 hydrogens on my reactant side. So that means I need 4 hydrogens on the product side. So the only way we get 4, I have 2 in one water molecule. So I've got to put a coefficient of 2 out front. 2 times 2 gives me 4 hydrogens now on the product side as well. Okay, so now my hydrogens and my sodiums are all balanced. Now what should I do next? Are we done? Are we all balanced? Let's check. I've got hydrogen, I've got SO4, I've got sodium, and I do have oxygen that I have to balance separate from the SO4, separate from the sulfate. So now I notice that I've got 4 hydrogens this side, 4 hydrogens that side. Sulfate, I've got 1 on the reactant side, 1 on the product side. Sodium, I've got 2 on the reactant side, and I also have 2 on the product side. Oxygen, this 2 that I've underlined right here multiplies the number of oxygens in sodium hydroxide by 2. So that means I've got 2 oxygens on the reactant side. How many do I have on the product side? I'm not counting these oxygens. Why? Because I'm treating them as part of a unit for sulfate. I'm just counting the separate oxygens. So I've got 2 times 1 means I've got 2 on the product side. So I am fully balanced. All of these numbers match up with all of these numbers. Okay, how are we doing? Am I moving too fast? Are you guys hanging with me? Are we good? Okay, we're gonna do some more practice. By the way, that was just rule number 1. Write correct formulas. So, number 2 is you add up the atoms on each side. Guess what? We already did rule number 2. Okay, and then you add coefficients to balance them. And my special note that I already talked about, but I just have it on this slide for you. Polyatomic ions can be treated as a single unit if and only if they occur in both sides on the reaction, in the reactants and the products. And that's what we saw with sulfate. It was on both sides, but guess what? Hydroxide was not. Hydroxide was present on the reactant side, but is not present on the product side. So we cannot treat hydroxide as a unit. That's why we broke up the oxygen and the hydrogen and we balanced them separately. Sulfate, we didn't have to break it up into sulfur and oxygen. We could just balance it as sulfate. So that was rule number 2. And we actually we already did all of that when we just wrote out the reaction. So I'm gonna scroll past that. That was rule number 2. Rule number 3, always double check that you're balanced correctly, which is what we did. When I wrote out all this stuff over here, that was me double checking my balance. And then rule number 4, this is always important too. You won't miss a lot of points for this, but if you forget to do this, you will miss a point. Reduce your coefficients to the lowest whole numbers. Okay, simplify. What does that mean? For example, if we had balanced it and we ended up with coefficients that were double what they should have been, so 2, 4, 2, 4, our reaction would still be balanced because we have the same ratio, but we can simplify all of our coefficients. We can divide everything by 2, right? 4 divided by 2, 2 divided by 2, 4 divided by 2, and that's where we would get 1, 2, 1, 2. All right, you cannot simplify 1. So if you have a coefficient of 1 anywhere in your reaction, then you cannot simplify. All right, but if you have stuff like 3, 6, 3, 6, or whatever, anything that you can simplify, make sure you do that. And if you simplify one coefficient on one side, you have to simplify all your coefficients by the same thing, okay? And that's why you saw I went through and divided everything by 2. So that's how if you have questions on how to reduce things, please let me know. If you divide one coefficient by a certain number, you have to divide all your coefficients by that number to simplify. Okay, let's do another practice. I want you guys to take a look at this chemical reactions. I want you to try to balance it, doing the 4 steps we just did. Well, number 1's already done for you. All the correct formulas are written. So start with rule number 2, balance by using coefficients, and then double check your balance, and then check to see if you can reduce your coefficients. If you're confused on where to start or what to do, I'll give you a tip. One thing, when I see elements that are by themselves, so example, chlorine right here is by itself. I save balancing chlorine for last. Anything that's by itself, save it for last. Because you can put a coefficient in front of chlorine here and it's not going to affect any other atoms. Okay, get your carbons and your hydrogens balanced first. Then you know you can balance chlorine last and you're not going to mess up anything you've already done with carbon and hydrogen. Okay, I see some of you kind of looking up like you're done. Some of you are still working and that's okay. Let's look at this one together. So I'm going to start with carbon. I'm going to balance carbon first. Anybody, what did you get for your balancing carbons? What coefficient should I put where? Any coefficients in front of any compounds with carbon? Should I put anything in front of CH4? No? Okay. We've got one here and one here. So they're balanced. So I don't need to mess with carbon. That's nice. Okay, what about hydrogen? I've got 4 hydrogens on my reactant side, but I only have 3. If I add up 2 hydrogens here plus 1 here, I've only got 3 hydrogens. So I've got 4 and 3. So that's not good. So how can I fix that? Riley says put a 2 in front of HCl. Okay. Now, hydrogens, when it comes to that, I've got 4 on the reactant side and total 2 and 2. Now I have 4 on the product side as well. I like that. Thank you, Riley. Okay, so now my carbons, we had 1 and 1. Carbons and hydrogens are both balanced. Now I can address chlorine. I see that I have 2 chlorines and 2 chlorines, because remember this 2 multiplies the number of chlorines by 2. So I have 2 from my first product and 2 chlorines in my second. So that means on the product side, I've got 4 chlorines. So what should I do to balance it on the reactant side? Put a 2 in front of chlorine there because I've got 2 in 1 chlorine molecule because it's a diatomic. So you would really mess this reaction up if when you wrote this, you only wrote Cl. It's a diatomic, so it has to be written Cl2, which is what you see in your typed reaction. So now when we put a 2 in front of that, we get 4 on each side. Okay? Okay, so there's the final thing. Any questions on that? And can I simplify? No, I cannot because I have an understood 1 right here. And I'm gonna bring something up that's gonna apply to the labs that you do this week. You're gonna be typing in your coefficients to Blackboard for your balanced reactions. It's often okay, like what you see us doing here, we're not writing in the 1. Okay, we're omitting writing in a 1. Yes, there's an understood 1 right here. But you can write it, you don't have to. On Blackboard, when you put your coefficients in, you have to type in the 1. Okay? Please make sure you do that or you're gonna miss a lot of points. So on Blackboard, type in the 1, but it's okay to omit a 1 when you're writing it on your paper. All right, let's do one more and then we're gonna move on to something else. Okay, looking at this, I noticed something. I noticed that we have polyatomics. I noticed hydroxide and I noticed phosphate as well. So you need to ask yourself, do I have both of those, hydroxide and phosphate, on both sides? If I do, I can treat them both as a unit. If I don't, then I can't. So go ahead and start. I would identify all the different elements you have. I see aluminum. I have hydroxide here, but I do not have it on the product side. So I'm going to treat oxygen and hydrogen separately, balance those separately. And then I do have phosphate, PO4, on both sides. So I'm going to treat that as a unit. So then take an inventory. What do you have on both sides? And where do you need coefficients and what do you need? All right, I'm gonna go ahead and start as well. Anybody have any first suggestions? Where do we need a coefficient?
A 3 in front of water.
Okay, 3 in front of water. So what did that do? Let's see. I noticed that I have this 3 applies to both of the elements right here. So starting out, I've got 3 hydrogens and 3 oxygens. Plus, I have 3 more hydrogens here. So I had 6 hydrogens starting out on my reactant side. So I really like this move because putting a 3 over here means 3 times 2 on the hydrogens there, 2 hydrogens in 1 water molecule, but putting a 3 means 3 water molecules. That gives me 6 as well. So now my hydrogens are balanced. Okay, good. Any other suggestions? Is everything balanced now? So let's check. We got 1 aluminum, 1 aluminum. I have 3 oxygens. So that was 3 on this side. And now this 3 means I've got 3 oxygens. And then I had 1 phosphate and 1 phosphate. So wow, that was relatively simple. I bet it didn't look simple getting started, but it wasn't too bad. Any questions?
Why didn't you count the oxygens in the second equation?
Right here,
Yes, ma'am.
because they're a part of phosphate. And so I'm not going to break those apart separately because I'm treating phosphate as a unit. I'm saying I've got 1 phosphate on this side and I just need 1 phosphate on this side and I already have that.
Okay.
That makes sense, Blake?
Yes, ma'am.
Okay. So that's why it's important to recognize your polyatomics. It'll really make things a lot easier for you if you do. Great question though. Okay, so that's some practice with balancing. Now we're going to look at classifying reactions, and these are going to, again, help us predict the products. If I give you 2 reactants, you could write the products if you get this stuff. So there's 5 kinds. These are the 5 initial kinds. Combination reactions, or you can call them synthesis. You'll hear both things. Here's what these look like. That means you have A plus B coming together. They're combining AB, okay? Often a key indicator is that you have more reactants on your reactant side, fewer products. So here we have 2 reactants, but we just end up with 1 product. But that's not the only scenario. You could have like A plus B plus C make ABC, okay? Or you could have 3 reactants making 2 products or something like that, okay? But regardless, things are combining. That's the point. If you recognize that things are combining together, we call that combination or synthesis. Okay, decomposition is just the opposite. You have something and it's breaking down into 2 or more things. Okay, so what we looked at earlier with the blood buffer reaction, we had carbonic acid breaks down into, in low pH environments, breaks down into bicarb and a hydrogen ion. That's decomposition. Or you could have 2 things breaking down into 3 things, okay? But as long as you have more products, fewer reactants, it's likely decomposition, okay? Notice how these 2, number 1 and number 2, are just the opposites of each other. All right, displacement, what does this mean? Sometimes people call number 3 a single displacement, and then number 4 is a double displacement. But you can just use displacement. You don't have to say single displacement unless I specifically ask you to say single displacement. Here's what that looks like. If I have compound AB plus C, C right here is by itself, and it is going to displace or replace one of the things in compound AB. So let me go ahead and write the products. But there's 2 ways you could do it. And how do we know? Is it going to replace A or is it going to replace B? Well, it depends. It depends if C is a metal or a non-metal, okay? If C is a metal, metals form what? Do they form cations or anions? Oh, come on. You guys know this. Thank you, Maria. Cations, okay? So the metal will replace the cation. So which one is the cation, A or B? In an ionic compound, we always write cations first. So the cation here is A. So metals are going to replace cations. So we would make Cb plus A. However, if let's rewrite it. I'm going to have to write it smaller because I didn't leave myself enough space. I'm going to scroll over here. If we have AB plus C, and C is a nonmetal, nonmetals form anions. Okay, except for hydrogen. Hydrogen's the anomaly, right? Nonmetals will replace anions. All right, so we're going to have AC because B is the anion. Anions are written second, plus B. All right, so you see there's two ways the displacement can happen depending on what C is. And C just represents an element that's by itself. All right, double displacement. Double displacement looks like this. You got compound AB plus CD. And the cation, this is often a key sign that you have double displacement is if you have two ionic compounds. All right, so if you have two ionic compounds, that is a key sign that you are going to get a double displacement reaction. So here's the cation. And then B and D are your, I'm just going to write A for anions. Okay. Or what you could write, probably what's actually easier, erase what I just wrote, unless you did it in pen, sorry. Do pluses and minuses. That would be better. That tells you what's the cation, what's the anion. You could write it above if you need to. So the cations are going to switch places and go with the other anions. So you're going to end up with AD plus, sorry, we got to write cation first. CB. And that's the only way it can work out. Remember to always write cations first. Anions are written second. All right, and then lastly, combustion. Give people a second to catch up. Combustion. So combustion to me is my favorite because it's so predictable. Number one, you get the same products every single time. So you always have some sort of carbohydrate, which is a compound that just has carbon and hydrogen in it. So I'm going to put, we don't know how many. It could be like C2H4, C2, C5H10. I don't know. There's so many different carbohydrates, but you get some kind of a compound with carbon, hydrogen, and then it's going to react with oxygen. All right. This is why we say cut off the oxygen supply to put out a fire. Don't blow on it. Okay, so it's going to react with oxygen. It's going to combust, and you get two things every time. You get carbon dioxide, and you get water. Okay, so if you see a reactant with a carbohydrate and oxygen, you automatically know your products are carbon dioxide and water. Okay, questions on these five? That's a lot, but this is all built on elementary. They're elementary to you now, principles that we've known and understand about cations and anions and things from ionic compounds. So we are about to get ready to actually put this and we're going to apply it to some real things reacting together. And we're going to write what they form. Okay, so this next slide is just that. So I want you to write the reactants. And this is very important that you remember what are diatomics and what are not. How do you write those if you need to? So you're going to write out these reactants, and then you're going to consider what kind of reaction could it be, and then you're going to write the formulas for the products. And then we're going to balance it. Are you having fun yet? Start with the first one. I'll do the first one with you. Magnesium. You're going to need a periodic table for this, by the way. Get one if you don't have one. Magnesium is Mg. This is a metal, but by itself, we do not write, it's not a cation when it's by itself. It's just the metal. So we don't write Mg plus 2. We just write Mg. It's not reacted with anything. And chlorine, how do we write chlorine?
Cl.
2. Thank you, Kylie. Cl2 is a diatomic. So you're going to mess up if you forget that. You're not going to balance it right. All right, so what could happen here? We have two elements by themselves. We don't have compounds, so nothing can break down any further because you cannot break an element down. So this cannot be decomposition. We have to have a compound, okay? These all represent compounds. We have to have a compound to do any of these other things. So it looks a whole lot like number 1. The only thing that can happen here is these two elements combine. We don't have any compounds yet, so nothing can break down or nothing can be replaced. So you're just going to get, how am I going to write we're going to have magnesium chloride. That's going to be our product. How are you going to write the formula for that? You need to ask yourself, what kind of cation does magnesium form? What's the charge? What kind of anion does chlorine form? What's the charge? How many cations and how many anions do I need to get a neutral compound overall? This is all stuff we did in chapter 3, remember? You're like, no, I forgot. Don't forget. So what's the formula for magnesium chloride? Anybody have it? What kind of, this is going to be a +2 cation. This is going to be a -1 anion. So we're going to need 2. Thank you, Brooklyn. We're going to need 2 anions and 1 cation. You can do the switch trick if you need to. MgCl2. Okay. Now, do we need to do any coefficients to balance it, or is it already balanced? Already balanced. That one's nice. We have the same number of magnesiums on both sides, same number of chlorines on both sides. All right, next one. Iron 3 bromide and hydrogen sulfate. We got to write correct formulas for these. This Roman numeral here indicates to me this is a transition metal cation. So that is going to be iron, Fe is iron, and that's going to have a +3 charge on it. Bromine is an anion. What's the charge on the bromine anion or bromide ion? Minus what? -1. And hey, word to the wise, if you're just sitting back watching me do all this, then chapter 5 is going to be really hard for you. Please, please pick up a pencil and do this with us, okay? I think most of you are, but if anyone's not yet, please jump in with us. All right. Okay, so how many do we need? Do the switch trick. For the formula, we need FeBr3. All right, plus hydrogen sulfate. We actually wrote this earlier, if you remember. This is H2SO4. How did I know that? I know sulfate is a polyatomic and it has a -2 charge. Hydrogen's main group 1, so it always forms a cation with a +1 charge. All right, so what could happen here? What kind of reaction is this going to be? Here's what I see. I see 2 ionic compounds. So which one is that? Which one did we write 2 ionic compounds by?
Double displacement.
So your cations and anions are going to switch. So the cation from the first compound, which is iron, is going to go with the anion from the second compound. So you need to write a compound for iron sulfate, iron 3 sulfate. So this gets exponentially more complicated from chapter 3. How do we write a formula for iron 3 sulfate? Okay, this has a +3 charge. Sulfate has a -2 charge. So do the switch trick. You are going to need two iron cations and 3 sulfate anions. Okay, so what that's going to look like is Fe2. And because sulfate is a polyatomic, remember your parentheses, SO4, 3. I know you might feel like I'm moving fast. So this is going to require practice to get efficient at it, okay? This is a lot of knowledge that we're combining into just writing these formulas correctly. All right, and then the other parts that go together is the cation from the second compound with the anion from the first. That's how double displacement works. Things switch. So we're going to write a compound for hydrogen bromide. Hydrogen's the cation. We know hydrogen is always a +1 and bromine's a -1. So I just need one cation and one anion. Don't worry about if it's balanced or not right now. You were just worried about writing correct formulas. So HBr, because that's a +1 and a -1. So you just need one each to get a neutral compound overall. Now, once you know you've written correct formulas, now you can begin to be concerned about, is it balanced? But I don't want you to worry about if it's balanced until you know your formulas are correct. So I'm going to try to erase very carefully here. Now we can see, how do we need to balance this thing? What do we need to do? Where do we need to put coefficients?
Two in front of iron.
Okay. Which side? Reactant side is what it looks like. I have 2 iron atoms on my product side, so I've got to have 2 on the reactant side. I've got sulfate on both sides, so I can, Brooklyn just went ahead and typed them all for us. 2, 3, 1, 6. Okay, let's see if that works out. 2, 3, I've got an understood 1 here. You do or don't have to write it. Okay, so now let's check. Irons, I'm gonna move up here. Irons, I've got Fe2 on that side, and I've got 2 irons on my product side. Bromine, so this 2 right here, I've got 3 bromines already in my compound, so 2 times 3 gives me 6 bromines on my reactant side. And when I put a 6 over here, that means I get 6 on the product side. Okay, and then what else do we have? Hydrogen and S-sulfate, SO4. So hydrogen, look right here. I put a, Brooklyn said put a coefficient of 3. I already had 2 in the compound, so 3 times 2, that means 6 hydrogens. And so that's perfect to put a 6 right there, 6 on both sides. Sulfates, I got this 3 here. So that multiplies my entire sulfate polyatomic by 3. So that means I got 3 sulfates there, and I already had 3. So that's great. Okay, questions on what we just did? This is the kind of stuff you're going to have to do on exam 2.
Wait, so like on like our like exam, how would we write this like an answer? Like,
Well, because Blackboard, Blackboard complicates things exponentially for me. So I have to plan very carefully what kind of questions I ask you. If not, before I know it, I would literally have 2,000 problems to grade. If I ask everybody 20 questions and you have to write stuff out for every, obviously you're going to have a lot of multiple choice on exams. So it might be just be picking from a multiple choice question which one's the right one, right? Or it might be fill in the blank style, type in your coefficients to balance it. So there's different ways I can ask you to test your comprehension of this. Probably, unless I ask one like file response question, or I have you write out the whole thing and write in your coefficients. But I'm not going to have a lot of those because I just simply can't afford in a timely manner to grade and return those to you guys quickly. So there's several different formats I could do. I probably didn't answer your question, Glenn, but I have to figure that out myself on how I'm going to ask you the best way. All right, let's look at the next one. Dicarbon tetrahydride. Whoa, this is a different kind of naming. We haven't talked about this. We talked about it in the video that I posted, but I've not talked about it with you yet. Here's what I noticed. The prefixes, di and tetra. This is a covalent compound. This is a binary compound. Dicarbon tetrahydride. So how do you write that? Di means 2, and it means 2 carbons. So that's C2. Tetra is 4, right? That means 4 hydrogens. So C2H4. This is a carbohydrate. And look, plus oxygen. So what kind of reaction is this?
Combustion.
Combustion all day long. So you already know your products. You don't even have to think. C2 and H2O. All or sorry, CO2 and H2O. Now let's balance it. You see why I like combustion the best? All right, so balancing, I see that I have two. I'm going to save oxygen for last, right? Oxygen's by itself over here. You can put coefficients in front of oxygen and not mess with your carbons and hydrogens. So balance your carbons and hydrogens first. So to do that, I'm going to put a 2 right here in front of CO2 because I already had 2 carbons on the reactant side. Hydrogens, what should I do? Any suggestions from anybody? Nadia
Two,
said
add a 2.
in front of water. I like that. Now that gives me 4 hydrogens on each side. Because I had 4 over here and 2 times 2 on the product side gives me 4 as well. Now let's check our oxygen. So carbons and hydrogens are both balanced. Now what about oxygens? Well, let's go to the product side first. Count up the oxygens on the product side first. You're going to have more. And then you can go back and put a coefficient in front of oxygen on the reactant side. So 2 times 2 means I got 4 oxygens there. Plus I've got this 2, which multiplies that by 2. So I got 2 more oxygens here. So 4 oxygens plus 2 oxygens is 6. This is not 60, it's 6 oxygens. So if I got 6 and I already got 2 in a molecule of oxygen, which by the way, this is a diatomic. That's why I wrote O2 and not just O. Now we got to have a 3 right there. 3 times 2 is 6. Okay, so you got 1, 3, 2, 2. We cannot simplify. Remember, always check to see if you can simplify. Okay, let's do these last 2. So we've done this was combination. Let's review for a second. This was double displacement. And then the next one was combustion. And now we have calcium chloride and oxygen. Interesting. Okay, calcium chloride. How do you write that? You got to know what's my ion or cation, what's my anion here. Ca2 plus is the cation. Chloride is Cl minus. So how do I write the formula for that? Do the switch trick if you need to. CaCl2 makes it neutral overall. And we got oxygen. Remember, oxygen is a diatomic. So we got O2 and not just O. Now you might think is this combustion? We got oxygen? Nope, because we don't have a carbohydrate. We got calcium chloride. Here's what I see. I see one ionic compound, and then I see an element by itself. So going
Single
back up,
displacement.
who said it?
Kristen, single displacement.
Single displacement. I like that, Kristen. I see a compound and I see an element. That looks a whole lot like number 3 I just circled. So single displacement. So then you got to ask yourself, is oxygen the thing that's by itself a metal or a non-metal? What is it going to replace? If it's a metal, it'll replace the cation. If it's a non-metal, it'll replace the anion. Oxygen's a non-metal. So oxygen is going to replace chlorine. So what you're going to form is calcium oxide. And oxygen as an anion, what does oxygen form? As an anion, it forms O with a -2 charge. Calcium is a +2, so you just need 1 cation and 1 anion. It's just CaO. +2 and -2 add up to 0. That gives me the neutral compound. Now chlorine is by itself. So do I just write Cl? No, it's a diatomic, right? So it's
Cl2.
Thank you, Cl2. Now, what do I need to do to balance this? Remember, I'm beating a dead horse here, but remember, always write your formulas first and then try to balance it. So I noticed that I have 2 chlorines on both sides. That's good. I got 1 calcium on both sides, but I have 2 oxygens on my reactant side, 1 on the product side. So that's the issue. So if I put a 2 right here to balance my oxygens, then I'm off on my calcium. So I got to come back over here and put a 2. Now my calciums are both balanced, but what does that do to chlorine? Throws that out of balance. because 2 times 2 gives me 4 chlorines here. I only have 2, so I can come over here and put a 2. Then everything should be good. And it looks like we're almost at time, so we got time for the last one. All it says is aluminum sulfide. What could happen here? Okay, aluminum sulfide, what is that? Al, what kind of cation does aluminum form? What's the charge on an aluminum cation? Brooklyn says 3. Yep, plus 3. Sulfide is sulfur as an anion, because IDE, remember, is how you name anions, and sulfide is a -2. So how do I write aluminum sulfide? Do the switch trick. Al2S3. So what could happen here? It looks like I don't even have a reaction. What kind of reaction could this be?
Decomposition.
That's right. Maybe this is just decomposing into its 2 elements. That's the only thing that can happen here. You don't have any other compound or anything for it to react with. So it's just going to form aluminum and sulfur. And are either one of these a diatomic? No, they're not. So you just write Al and S. And now you just balance it. 2 and 3. Okay. That's as far as we're going to get today because we are at time. I had a few